So if you've taken high school chemistry, you've probably heard of the term electron configurations before. You probably, in fact, did that. If you didn't learn electron configurations before, or you didn't take high school chemistry, that's totally okay because electron configurations are actually fairly simple once you learn the rules. So before we do some examples, let's learn the rules. So the first one is going to be the Aufbau principle, also known as the building up rule, which basically says that when you're building up electron configurations, you place electrons in order of increasing energy. All right, so you're going to start from the bottom and move up. Right, it's kind of like a flight of stairs. You can't get to the second floor until you go through the first floor, and you can't get to the third floor until you hit the second floor. Same thing, right? You can't reach a shell that's really far away until you fill the shells that are closer and lower energy. So that's Aufbau. The second rule that you'll follow when building up electron configurations is that it's called the Pauli exclusion principle, and it basically says that no two electrons can have the same four quantum numbers. Remember, there's four quantum numbers. Think of these quantum numbers as an identification number, right? An ID for the electron, like a social security number. You can't have two electrons that have the same social security number, right? So all electrons will differ in a given atom. And how many electrons per orbital? Only two. So no more than two electrons per orbital. And within an orbital, the spins must be opposite. All right, so opposite. So as we've seen before, one is going to be spin up, plus 1/2, one spin down, minus 1/2. The last rule is Hund's rule, and basically says that when you add electrons to a subshell, they'll always occupy an empty orbital if one is available. All right, and what'll happen is electrons will only pair if there are no empty availables available. So let's look at a quick example. So let's say you have a D subshell. All right, so D subshell. So at this point, you should know how many orbitals there are in a D subshell. Right? D means L equals 2. So ML ranges from -2 to -2, -1, 0, 1, and 2. So there's 5 orbitals in a D subshell. The way that you add electrons to this subshell is the following. So you add the first electron will go in the -2. The next electron will not go in the same orbital. It'll go into an empty orbital, right? You add a third electron, it goes into the empty orbital, and so forth. Until no more empty availables are available, they're forced to pair up. So the way I'm drawing these out is the way that the electrons will be added to a particular subshell. You should know this. This is very important. In fact, all 3 rules are important. You should be familiar with the names as well as what each of the rules says. So now we know the rules. Let's look at the periodic table and basically figure out what we need to look at when we're solving for an electron configuration. So there's 4 aspects of the periodic table. There's an S block, D block, P block, and an F block. You should remember this for the test because this will not appear on your exams. Whenever you're building electron configurations, you basically start from the top. So you build electron configurations from left to right, 1 row at a time. It turns out you sometimes don't actually have to start from the very beginning because you can use abbreviations using noble gas configurations. When we do some examples, I'll show you exactly what I mean by that. There are kind of some weird anomalies here. If you look in this 4th row, you have like the S block, and this is 4S. But when you move to the D block, you go to 3D. So that's one kind of anomaly where the 4th row of the D block corresponds to 3D, not 4D. Notice that for the P block, it's the same as the S block. There's also an anomaly for the F block. It's not shown here very clearly, but this F block actually starts in between 6s and 5d, and so only elements after 6s will have electrons in the F block. It turns out the 6th row corresponds to 4f, not 6s. So essentially for the D block, you subtract 1, for the F block, you subtract 2. For the purpose of your class, F block is not tested very often. Really, you just have to know the S block, D block, and P block. So let's try some examples. So it says write the full electron configuration for the following atoms. The first one is sodium. So we find sodium. So sodium is Na. It is right here on the periodic table, atomic number 11. So as I mentioned before, you build from left to right. So you start from the very beginning. This is the S block. And actually, it turns out helium is also part of the S block. So I'm going to call it 1S2 because I had to move over 2. And then I move to the next row. I'm in my S block. I write 2S2. I move all the way to the next block. That's P. I write 2P. I have to go 1, 2, 3, 4, 5, 6 elements. So I write 2P6. And then I finish off on my third row, S block. So I write 3S1 because I'm ending on sodium. And if you actually add up all these numbers, 2 plus 2 plus 6 plus 1, that gets you 11, which is the number of electrons that the atom has. All right, so let's try nickel. So we find nickel. Nickel's in the D block right over here. Here they're asking for us the full electron configuration. So let's start from the very beginning, and it always starts the same way. So it's going to be 1s2, 2s2, 2p6, 3s, and here we're passing it. So we're going to write 3s2. We're passing sodium. We go to the p block, so 3p6. 4s2, and then we enter the D block. And remember that the D block is weird. It's not going to be 4D, it's going to be 3D. And I move 1, 2, 3, 4, 5, 6, 7, 8 elements over. So I write 3D8. And a lot of times what will happen is, by convention, you want to write these numbers in increasing order. So rather than write 4s2 before 3d8, you actually want to switch these two around. Right, so the better way to write this would be to say 3d8 and then 4s2. So 1s2, 2s2, 2p6, 3s2, 3p6, 3d8, 4s2, and that's your electron configuration. So switch it. Turns out, if we were to do a full electron configuration for very large atoms, that would take forever. So we can have abbreviated electron configurations in which we use the noble gases. So for cobalt, let's give that a try. So we find cobalt, and where is cobalt? Right here. Basically, look at the noble gas right before, which is going to be argon. So I can write argon in brackets. And essentially, I just continue my electron configuration from there. So I jump to 4s2, and then 3d 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 3d7. Right? We can do the same thing for radium, right? Radium is all the way down here. It would take forever if we did full electron configuration. We can just write the noble gas right before, which is radon, Rn, and then we're on row 1, 2, 3, 4, 5, 6, 7, so we write 7s2. And then finally, we can do tellurium. Te is right here. The noble gas before is going to be krypton, so I write that in brackets. I move to the next row, which is row 5, S block, so 5s2. And then I get to 4d, right, because I subtract 1, 4d, 10, and then 5, 1, 2, 3, 4, 5p4. And then remember, just switch these guys around, right? Because you want the 4 to come before the 5. So we write 4d10, 5s2, and then 5p4. And that becomes important when you talk about ions, because it turns out that the higher the number, the higher the energy, and you remove electrons from high energy to low energy. So there's two types of ions. There are anions and cations. Anions are negatively charged, if you remember. And so that basically means you add electrons until the next noble gas configuration is achieved. For cations, you remove outermost electrons. And so for whenever you're doing electron configurations of ions, don't just assume you can move to the left or the right on the periodic table. Instead, you should write the electron configuration of the original element and then add or move electrons accordingly. So I'll show you what I mean by that. So let's start with the abbreviated electron configurations for the following. So let's start with sulfur. This is not an ion, just an atom. So we'll start by looking at where sulfur is. So we got to find sulfur. So sulfur is right here. The abbreviated electron configuration is going to be neon, 3s2, and then 3p4. That's of the neutral element. If I add 2 electrons, right, the 2 minus means I'm adding 2 electrons, I add them to the P, right, because my S is already filled. So basically it becomes neon 3s2, oops, that should be a 3, 3s2, 3p. Instead of 4, it's going to be 6. Now, you could also write your answer as argon, right? Because by adding 2 electrons, you have the same number of electrons as argon. We call this sulfide ion, S2 minus, isoelectronic with argon because it has the same number of electrons. So either two of these answers would be correct. So let's try neutral iron. So iron is right here. The normal gas before it is argon, so we'll write argon in brackets. And then we'll write 4s2. That's actually, we're going to write that afterwards. So we're going to write 1, 2, 3, 4, 5, 6. So we're going to write 3d6 first, and then 4s2. And that's important because when we do the electron configuration of Fe2+, we remove 2 electrons from 4s before 3d, always. You always remove from 4s before 3d. That's a very important, very common mistake. So remember that. So instead of writing AR 3d6 4s2, we just write AR 3d6 because the 4s2 is gone. We lost 2 electrons. And then for Fe3+, we're losing an additional electron on top of the 2 that we just lost, so it's going to be 3d5. All right? Okay. And one thing to point out here is that there are 5 electrons in the d subshell. Remember that the d subshell has a total of 5 orbitals, and it can hold 10 electrons. So what Fe looks like is this. Its d subshell is half filled, and it turns out that a half-filled subshell is unusually stable. Okay? And this is important in the next slide when we talk about exceptions. All right? So the exceptions are full and half-filled d subshells. Okay? So for a half-filled d subshell, if it has 5 electrons, if ever you have 4 electrons in a d subshell, you're going to steal 1 electron from the s orbital in order for the d subshell to have 5. Same thing happens if you have 9 electrons in the d subshell. You're going to want to steal 1 electron from the s orbital, so now you have 10. Now this only happens really for 2 elements on the periodic table, chromium and copper. So chromium is located right here, and copper right here. Turns out all the elements underneath as well follow the exceptions. Really, for the purpose of your class, chromium and copper are what appear most often. So for chromium, normally what you'd think the electron configuration is, if you didn't know the rule, you might write argon, and then you write the 3D first. So write 3D1, 2, 3, 4. So you'd write 3D4 and then 4S2. If you didn't know the exception. But what's going to happen here? You have 4 electrons in D. What do you want? You want 5 electrons. So it's going to steal 1 from the S and add it to the 3D. So this is not the right answer. The right answer is going to be argon 3D5 4S1. So that's the electron configuration of chromium because half-filled subshells are exceptionally stable. Same thing happens for fully filled. For copper, you would think it's going to be argon 4s, or let me write the 3D first. So you would write 3d9 4s2. Nope. The s electron goes into the d, so this is wrong, and your real answer is going to be argon 3d10 4s1. These are the only exceptions. Don't try to apply this logic to other elements. It doesn't work the reverse, where if you have 3d6, it'll donate to the 4s, right? It only works this way. So chromium and copper exceptions, you should memorize those.